Swayam Prabha. Digital India. Educated India.
Welcome everyone to lecture 6, and as I said, we are going to continue with the angular momentum balance derivation. Okay, so we had already derived the contribution to torque due to tractions on the 6 faces of the cuboid and due to the body force, and we have to equate it to rate of change of angular momentum of the cuboid. Okay, so let us try to derive that term today. So, we have to derive d by dt of angular momentum of the cuboid about its centroid. Okay. So, let me redraw the cuboid. So, here is the center of the cuboid x, and think of any other point y in the cuboid. Okay. So, what is going to be the angular momentum of the cuboid about its center? So, h about x. So, first of all, if a particle is moving with the velocity v, then what is its angular momentum? So, for a particle, it is simply position vector of the particle relative to the point, let us say O, about which we are measuring the angular momentum, cross product the momentum of the particle. So, that is m times v, right. All right. Now, in this cuboid, which was a part of the body, it has got several small particles. So, we have to sum over all the particles. So, it has infinite particles, we have to have a triple integration, right. So, therefore, we will have triple integration, and then we have position vector of let us say point y relative to x. So, that is y minus x cross product the momentum of the particle at y, and that momentum has to be measured relative to the center of mass. So, in the center of mass frame, remember we are doing things in the center of mass frame. So, the momentum of that particle is simply the mass, which is d m, because it is a small particle. So, mass is d m times the velocity of the particle y and relative to the center of mass, which is x, right. Okay. And then d m, we know it is rho times the d v. Okay. So, we could also write it as triple integration y minus x cross product rho v relative to x d v, the small volume, which in this case is d eta d zeta d gamma, right. Okay. Now, you see in this integration, we are doing integration over the volume, and then we have to take its time derivative. Okay. That is really tricky here. See, whenever we apply Newton's second law or the angular momentum balance, it has to be applied to a fixed set of mass or the fixed set of particles. The mass should not change, we have to apply it to an identifiable mass. Okay. Now, problem with this cuboid is the mass contained in the cuboid at a given time is something, and at a later time it is something else, because mass is transporting through the cuboid, right. If you do the integration in the volume domain, then the volume is a function of time then, because as the mass is flowing, the volume of that set of mass is also changing with time, is not it. So, this volume here is a function of time. So, whenever we do d by dt of this quantity, we have to take into account the change in volume also, right. So, we can now move back to the control mass setting, which we have earlier, dm. Instead of dv, if we do dm, so we are integrating over the mass. So, mass is now identifiable and mass is not changing, right. So, this is control mass, whereas this is with control volume. So, now when we do d by dt of the angular momentum relative to center of mass, so d by dt now goes inside the integral, because now the integration domain is the mass. Okay. So, here it is mass, and then we will have d by dt of y minus x cross dm velocity of the particle y relative to x, right, plus y minus x cross dm into dv by dt, d by dt of velocity relative to x, which is nothing but acceleration of y relative to x, right. So, in the center of mass frame, that is the acceleration. Okay. And now, you have to see the first term here. Look at this term. So, this term is velocity of y minus velocity of x, which is velocity of y relative to x, right. So, this is velocity of y related to x, and we are crossing it with velocity of y relative to x. So, it cancels, right. So, therefore, this term cancels. Also notice that we did d by dt of y minus x, d by dt of velocity, we did not do d by dt of dm, because mass of the particle is not changing, right. So, it is fixed, it does not change with time. Density can change, volume can change, but mass of a particle does not change. Okay, now, the first term is gone. So, we have to now look at the second term, and now we can switch back to the volume integral. From mass integral, we can switch back to volume integral, because time derivative is already inside. Okay. So, I will write this as triple integral over the volume, okay, the volume of the cuboid, then y minus x cross product, and then dm becomes rho dv, right. So, rho times acceleration of the particle y relative to x times dv, which is what, d gamma, d zeta, d eta. Okay. Now, can you see this is very much like the body force term, where B is replaced with rho A y, right. So, basically this term here, so it was earlier the body force B of y, otherwise the integration is the same. So, using the similar logic as for the body force, you do its Taylor's expansion, work out the integration. Finally, it is going to be of the order of small o in volume. Okay. So, this is finally of the order of small o in the volume. Okay, that is a small o. So, it decays faster, it goes to 0 faster than the volume of the cuboid. So, now we have everything. So, we can now write down our angular momentum balance equation. So, you have to now recall the total torque external, that is equal to d dt of angular momentum of the cuboid relative to the center of mass x, and then the torque external has got contribution from the traction and from the body force, and from the traction, if you recall, it is summation I equal to 1 to 3 E I cross sigma E I times delta V plus the contribution due to the body force term, which is small o of delta V, and that is equal to the rate of change of angular momentum, that is also small o in delta V, right. So, that is the equation. Now, as this equation holds for any cuboid, so why do not we again shrink the cuboid to its centroid? Okay. So, make the cuboid smaller and smaller and shrink it to its centroid or to its center x. So, when we do that, we can now divide this whole equation by delta V and take the limit delta V going to 0. Okay. So, here basically we are shrinking the cuboid to its center small x. Okay. So, what is going to happen in this limit? So, small o delta V by definition it goes to 0 faster. So, these terms go away, and finally, what is remaining is very simple, that E I cross sigma E I and summation, that is equal to 0. Okay. So, that is the final equation of angular momentum balance, and as I told you, this equation holds even if body force is acting or the body is accelerating. Okay. So, let us see what is the meaning of this equation. Let us try to write it in the component form in the coordinate system of E1, E2, E3 and see what we get. Okay. So, now it has got 3 terms I equal to 1 to 3. So, for each of them we have to write it in the component form. So, first is E 1 cross sigma E 1. What is E 1 in the E 1 to E 3 coordinate system? That is simply 1 0 0. So, we get 1 0 0 cross sigma E 1, and sigma E 1 is simply going to give me the first column of sigma matrix, which is sigma 1 1, then tau 2 1 and tau 3 1. Okay. Plus the second term E 2 cross sigma E 2, and then the last term E 3 cross sigma E 3, which is the third column of sigma, and that is tau 1 3, tau 2 3 and sigma 3 3, and this is equal to 0. Right. Let us work out the cross product and see what we get. So, the first term you work out the cross product, and this gives us 0 minus tau 3 1 and tau 2 1, right. Then the second term, that is going to give me tau 3 2, then 0 and minus tau 1 2, right. And then the third one, that gives us minus tau 2 3, tau 1 3 and 0. Okay. And this is then equal to 0. So, you see we get 3 conditions from here, which implies that tau 3 2 is equal to tau 2 3. Similarly, tau 3 1 is equal to tau 1 3 and tau 2 1 is equal to tau 1 2, okay, which is basically saying that the stress matrix has to be symmetric. Okay. So, that is the final outcome of angular momentum balance, that the stress matrix has to be symmetric. Okay. So, this implies that the stress matrix is always symmetric. And if somebody asks you, is this going to happen even if the body is accelerating, then yes, of course, because this derivation works even if the body is accelerating or the body force is present. So, I will write here holds even if the body is accelerating. Okay. You know, there is also a simpler way to come at this final derivation, which you will find in many textbooks. Let me show that derivation to you. It is slightly more physical. So, let me redraw the cuboid, okay, and think of this coordinate system E 1, E 2 and E 3. So, on the E 1 plane, you visualize that stress matrix representation. So, here on the even plane we have sigma 1 1 and then we have tau 2 1 and we also have tau 3 1, right. Similarly, you go on the top plane and you see you have sigma 2 2, then we have tau 1 2 acting in the positive one direction, and we have tau 3 2. Right. And likewise on the bottom face also you can go and you have those 3 components of traction. So, you have sigma 2 2 and then you have tau 1 2, but now this acts in the negative one direction because it is the negative 2 plane. So, it acts in the negative one direction. So, it is going to be tau 1 2 and then you have tau 3 2, which is now in the negative 3 direction. Okay. There are of course many more faces remaining. Let me do it just for the negative 1 plane. So, on the negative 1 plane sigma 1 1 pointing towards the negative 1 direction. So, on the negative plane everything points in the negative direction, on positive plane everything points in the positive direction. Okay. And then we have tau 2 1, but now it is going to point in the negative direction. So, we have tau 2 1 and tau 3 1. Now, let us try to find out the moment due to these tractions about the E3 axis. So, what is the moment about E3 axis and passing through the centroid or through the center of the cuboid. So, we want moment about E3 axis. You see sigma 1 1, sigma 2 2, they are all passing through the centroid. So, it does not contribute in any moment about E3 axis. Tau 3 1, tau 3 2, they also will not contribute to moment about E3 axis because they are acting in the E3 direction, right. Tau 3 1 or tau 3 2, they are acting in the E3 direction, but tau 1 2 and tau 2 1, they are going to contribute to moment about the E3 direction. And can you see what will that be equal to? See, due to tau 2 1 on positive E1 plane, it contributes in the positive direction, and also due to negative E1 plane, that tau 2 1 also contributes in the positive direction. So, what is the total moment? So, it is going to be tau 2 1 times the area of the face, which is, so this is the E1 plane. So, its area is delta y into delta z, right, or in our earlier notation you could say delta x 2 into delta x 1. So, that is the total shear force on the E1 plane along the second direction, and I want the moment about the centroid. So, the arm is simply delta x 1 by 2, right. Sorry, the area here is delta x 2 into delta x 3, not delta x 2 delta x 1, and the arm is delta x 1 by 2, and similar contribution also comes from the negative even plane. So, we get 2 times this, right. The whole thing is then multiplied with 2, and similarly we have contribution due to tau 1 2. So, I am going to say it as, and you see the tau 1 2, in which direction does it contribute? It contributes along the negative E 3 direction, the sense is in the negative E 3. So, it comes with a minus sign, minus tau 1 2 times delta V, okay. And so, finally, this is simply tau 2 1 minus tau 1 2 into delta V, right. So, that is the moment. Then you find the moment due to body force about E 3 axis, that will be of the smaller order, and then the rate of change of angular momentum about E 3 axis, that is also going to be of smaller order. So, this is as a whole equal to 0, which means tau 2 1 is equal to tau 1 2. Okay. That is a simpler derivation, but of course, here we said that the tractions are not varying in the plane, right. We just said there is some tau 2 1 which is the same everywhere in the plane. So, that is a simpler derivation which somehow works. Likewise, when you find out moment about E 1 axis, that is going to give you tau 2 3 is equal to tau 3 2, and moment about E 2 axis, that is going to give you tau 1 3 is equal to tau 3 1. Okay. So, that is a simpler derivation giving you the same result finally. Okay. So, basically the take home message from here is that the stress matrix or the stress tensor is always going to be symmetric. Okay. And this leads to several simplifications you will see later on. Let me work out an example. So, suppose I have an arbitrary body which is clamped somewhere, and then you are applying traction, or let us say you are applying load on some part of the boundary. Okay. And say this load, which is force per unit area, its magnitude is T naught. Okay. So, this is externally applied, it is applied by something which is not a part of the body, externally. So, I will write here applied by external agent. So, now the question is, what can you say about the state of stress at points in the body which are very close to the surface where we are applying the traction. Okay. So, basically I want to know what is the state of stress at these points. Can we say something about the state of stress here without solving the stress equilibrium equation? If you solve the stress equilibrium equation, you can find out stress everywhere in the body, but I do not want to do that. Can we directly get it through some physics? So, to figure it out, let us draw a coordinate system such that we have E 3 axis along the surface normal. Okay. So, draw the part of the body near the surface. Okay. Okay, so that is a part of the body, and the top one is the surface on which we are applying this T naught, and assume that this is really small. So, T naught is almost constant on the top surface, okay. And choose the coordinate system such that your E3 is along the surface normal. Okay. So, E3 is along surface normal, and then E1, E2 are in the tangent plane of the surface, are in the plane of the surface at that point. So, we have E1 and E2. So, these two are in the tangent plane at the surface point. Okay, so, basically for every surface, so here is the surface. So, at this point, for example, the tangent plane is this. Think of a tangent just touching the surface. Think of the plane just touching the surface, that is the tangent plane. Over here it is this. So, E1 and E2 are in the tangent plane, and E3 is along the surface normal. So, E3 is the normal of the tangent plane. Okay, so, we set up a coordinate system like that, and then think of the tractions which are acting on the faces of this small part of the body. Bottom face is negative E3 plane, right. So, there we are going to have T minus 3, and likewise we have other faces also, is not it. So, suppose that the lengths are, so this for example, suppose this is delta 1 and this one, that is delta 3, okay, and this one, that is delta 2, all right. So, given that dimension, what is the total force due to the tractions on this small box? So, we have T minus 3 acting on minus E3 plane, and what is the area of that surface? That is delta 1 into delta 2, is not it. Then we have T 2 and T minus 2 acting on the E 2 and minus E 2 planes. So, we have plus T 2 plus T minus 2, they are acting on E 2 and minus E 2 plane, and what is the area of plus E 2 and minus E 2 planes? That is delta 1 into delta 3. And then think of the other two planes. So, T 1 and T minus 1. So, T 1 plus T minus 1, and what is the area of those faces? That is delta 2 into delta 3, right. So, that is the total force on this box, this is small box. Then you will have body force also on this small box. So, that is going to be equal to some body force B times the volume of this box, which is delta 1 into delta 2 into delta 3. But you see, we have not yet taken into account the force by the external load, the T naught, which is acting on the top surface. So, we have to also include that. So, plus T naught times the surface area. Now, that is curved, but because it is very small, you could write it as delta 1 into delta 2, right, delta 1 into delta 2, and this has to be equal to mass times acceleration, net force equal to mass times acceleration. So, mass is rho into the volume, which is delta 1, delta 2, delta 3 into acceleration A. Okay, so, that is the Newton's second law. For this small box, some people also call it pill box. Okay. But what I am going to do now is I am going to shrink this pill box so that only delta 3 is reducing. Keep delta 1 and delta 2 fixed, but just reduce delta 3. Physically, what I am doing is I am getting close to the surface. The bottom plane, the negative E3 plane, I am pushing it to the surface, right, as delta 3 goes to 0. So, let us divide this whole thing by delta 1 delta 2 and then take the limit delta 3 going to 0. So, I will write here by letting delta 3 going to 0, we are shrinking the box or let us say the pill box, so that the bottom surface of the pill box gets close to the surface of the body. Okay. Now, can you see what is happening in that limit? So, we will have t minus 3 plus t naught plus t 2 plus t minus 2 times delta 3 by delta 2 plus t 1 plus t minus 1 into delta 3 by delta 1 plus b minus rho times acceleration into delta 3 equal to 0, right. And you see for each of the terms here, delta 3 is going to 0, delta 1 and delta 2 are kept fixed, but small, but delta 3 we are really letting it go to 0, because we want to get close to the surface. So, you see all of these go away, and finally, we get traction on negative 3 plane is equal to minus of t naught, or traction on positive 3 plane is equal to t naught, right, because traction on 3 plane and negative 3 plane are action reaction pairs. Now, this result might look very intuitive to you. You could have guessed it perhaps in the beginning itself, but you realize what is traction? Traction is the force per unit area applied by one part of the body on the other part of the body. So, it is applied by the body itself on its other part. So, it is an internal force per unit area, whereas T naught is applied by the external load, external agent. I mean, you can't really say that T naught could have been T3 right in the beginning, because they are two different things. Traction is the internal response of the body, whereas T naught is by the external load or by the external agent. But this derivation just tells us that the internal response of the body close to the surface is same as what the external agent is applying. So, we can only say about T3, not about T1 or T2, we are only able to say about T3. Okay. So, if we now think of forming the stress matrix for a point close to the surface, what is that going to be? So, for a point close to the surface with the coordinate system that we have chosen, the third one is T naught, right. The third one, the third plane or the third column, which is formed by the traction on third plane. So, that is T naught. So, this is known to us, but what is on the first and second column, that is unknown to us. But the third component of the first and second column will get known because of the symmetry of stress matrix. So, this one and this one, they are same as what is here and what is here. This is all you can say about the stress matrix at points which are close to the surface. So, you know about 5 entries here, but 4 of the entries are unknown, which you can find by solving the stress equilibrium equation, but remaining you can guess right away. If the surface is traction free, then what happens? So, you see there are many parts of the surface where you do not apply anything, like this part there is nothing, right, there is no traction acting, and that is a whole domain, there is whole boundary of the body, lot of boundary, right, where there is no traction or there is no load applied by the external agent. So, T naught is basically 0. So, if the surface is load free, then what can you say about the stress matrix? So, in that case, so I will write here, if the surface has no external load, or T naught is equal to 0, in that case it is a special case, and you could simply say that this part is 0, this part is 0, this component is 0, and from symmetry these two components are also 0, but these 4 we do not know, but remaining all are 0. Okay. So, we have lot of information about stress matrix just by knowing the boundary condition. Without solving the equation, just from the boundary condition you can tell about the stress matrix on the surface. Okay. There is another interesting case. Think of a static fluid, let us say a bucket of water. So, we have water inside, and we know from our school that the pressure in the water, as we go down, it increases, right. Pressure is equal to rho g h. So, pressure P is equal to rho g h, where h is the height from the top surface or the depth from the top surface. Now, what can we say about the state of stress at any point in the water body? So, what about the state of stress at any point in the water body? So, so you go to any point and you know that the pressure there is rho g h. Think of any plane at that point, a small infinitesimal plane at that point. Suppose this plane having normal along some direction. So, what is the traction on that plane? It is the same pressure. Fluid cannot sustain shear when it is in static equilibrium. Okay. So, fluids do not sustain shear. I will write here. When in equilibrium, let us say it is static. So, you take any plane at that point, on all the planes there would be no shear and the traction would be that same pressure P. So, since there is no shear, we only have normal component of traction on all the planes at any point in the fluid body. So, this means at any point in fluid all planes passing through that point have only normal component of traction. Okay. What does this mean? So, T at any point x in the fluid body and on any plane n, where n is the surface normal direction, that is equal to. So, the traction has to be along the normal itself. So, of course, we know the direction, that is n, and what is the magnitude of traction? That is the pressure itself, P, and because we know pressure is compressive, so it comes with a minus sign. Okay. So, on any plane T is simply minus P n. So, if that is the case, what can you say about stress matrix? What will be stress matrix? Sigma matrix in E1, E2, E3 coordinate system. So, on E1 plane the traction is again normal. So, only the first component is minus P, the shear components are all 0. So, this is minus P 0 0. On E2 plane it is 0 minus P 0. On E3 plane it is 0 0 minus P, which is minus P times the identity matrix, right, identity matrix. Which means that the corresponding stress tensor sigma is minus P times identity tensor, and that is why when you compute T, as sigma times n. So, T we know is sigma times n, which is minus p into identity times n, which is simply n, right. Identity gives you the same vector minus p n, that is what we wanted, right. So, the stress tensor for a fluid body in statics is simply minus p times the identity. All right. So, I guess with this I will finish this lecture, and in the next lecture we will discuss about what is called the principal planes and principal stress components. Okay. So, thank you.